Hi! Let's now close Module 9, Renewable Energy Forecasting First Steps, with this third block, Digging in the Data. In the previous block, we've been through linear regression, and we saw how this may be used to model a relationship between explanatory variable and a response variable of interest, say power generation, over a time window in the past. Then this relationship can be used for predicting the value of the response variable in the future with input future values of the explanatory variable. Obviously, we need this future value of explanatory variable, and this justifies that here in a more general context we'll use some forecast, weather forecast, as input to our problem. Also, we discussed the concept of linear regression with one or a limited number of input variables, explanatory variables. However, in a more realistic case, in view of the wealth of data that's being collected today, one may have access to a lot of variables. And we'll even discuss the fact that there's more than just these variables, and we can derive features that can be combination of variables, some other variables you may not have thought of in the first place, etc. So in this block, we'll consider the more general case of digging in the data and building some models that is usable for forecasting. For a simple test case of a wind farm, what do we have in terms of data? We have measurements, so that's the power measurements at the level of the wind farm, YT. We have weather forecast, that can be wind speed forecast, U hat T plus K given T. We have wind direction forecast, theta hat T plus K given T. And we have temperature forecast, uppercase T hat T plus K given T. These are the base input variables that we have for our problem. As I said earlier, even though we have these variables, we may be able to define features that can be either a combination of these variables or different interpretation of these variables. For example, even though wind speed is a direct input variable that can be used as input to our problem, we may also take the power of wind speed forecast. So that means that we elevate the wind speed forecast to the power of 2 or to the power of 3. And we can use that directly. So this will be seen as nonlinearities, even though since we're going to have linear coefficient times this variable, we're still going to have to handle a linear model. Also, for instance, wind direction is a polar variable, since obviously the wind direction is just going around like that. So it may be interesting to reinterpret the wind direction in terms of harmonics, so that would be cosine and sine of 2 pi the wind direction forecast divided by 360. What is interesting with harmonics is also that you may have different value here in the denominator, so that might be 720, 180, so that you can control the period or the frequency of your harmonics and give some value as input to your model. Also, there might be some features that are actually variables that you didn't think you had in your wallet in the first place, but that were always available. For instance, there's also the hour of the day here as a variable that's available and of interest. We explained in a previous block that in certain areas of the world, the winds can be highly influenced by the time of the day. That's this thermal effect. There may be also an interest to consider the lead time if there are some effects that we can better model for short lead times, but not as good for longer lead time. There may also be some other features that are not listed here that you may think of. All these variables that we obtain eventually, directly the input variables or some features that we derived, we denote them by xj, and we have m of those, and we call them features. Now that we have our features, we go back to our linear regression framework. Remember that linear regression consists in a linear relation between these xj explanatory variables and the response variable y. So for each and every time instant I, we can write a relationship between the response variable value, and it's linear with an intercept term and linear coefficient times the value of each and every explanatory variable. Besides this linear relationship, there is also a noise term, epsilon I, and we assume that this noise term is Gaussian and centered on 0. So there's no systematic error, if you want. Eventually, we will want to minimize the value of this noise, and that's the point of the least square estimation we'll be considering. Equivalently, we can write this relationship in a compact form, as it will be easier to handle. So now that we've reformulated it in a compact form, we have yi equal bold beta transpose times bold xi plus the noise term, and there beta is the vector of all our linear coefficients plus the intercept, and then bold xi is a vector that contains the values at time I of all the explanatory variable plus a coefficient 1 that relates to the intercept. We want to have the best value for beta, and that's why originally we introduced this least square estimation framework, but also we would like to use the minimum of those variables. That's the parsimony principle. You want to develop and use models that use the minimum set of information as input. It will help you avoid overfitting, and most likely it also helps you select what's the important information to use as input to your problem. Least square estimation is not made for that. Least square estimation is just made to minimize the noise, the residuals that you have in your model, so eventually the forecasting error in a quadratic sense. If you were to use least square estimation to fit your model with a large number of variables, you would get values of coefficient for all those variables, most likely, and then you would have a super high dimensional model. But there is something else that can be used. It's called the lasso, and the lasso is a generalization of this least square estimate so as to penalize the parameters and their estimate, and so as to have the minimum number of those parameters being non-zero. Formally, if we were to introduce this lasso estimate for linear regression model parameters, it is given by the minimization over beta of a scaling times the quadratic loss that we had before, so the sum of the squared residuals, plus, and this is where it gets interesting, we also try to minimize the L1 norm of your model parameters. So the L1 norm here is the sum of the absolute values of your parameters. So you're going to try to push them down and as many as possible of them being equal to 0. We have a term here, lambda, which is referred to as the regularization parameter, and that will control the trade-off between the residuals that you want to minimize, the quadratic loss here, and the L1 norm of your model parameters. Here, eventually, what we'll get is a set of estimates, beta hat, so that's the estimate of all our parameters. X, we will write the design matrix as we use for the least square estimator. So it has a vector of 1, and then it has successive vectors for all the fixtures and the time instants that were collected in the past. And then we have a vector y with all the past values of the response variable. Now, if we want to get a lasso estimate for beta, we can also use functions in R, MATLAB, and some other languages that permit to readily give you the lasso estimate. Let's look at an example based on a set of features. We've gone not so crazy here, so the number of features is still quite limited, but it will be a fairly representative case. So we describe y at any time instant with a linear intercept, a linear coefficient times the wind speed forecast, another coefficient times the square of the wind speed forecast, then another coefficient times the cubic value of the wind speed forecast, then another coefficient times the harmonics, so the cosinus component of the harmonics for wind direction, another coefficient times the sine component of the harmonic, So that's the same value inside, function of wind direction, but we have the cosine here and the sine there, plus another coefficient times the temperature forecast, plus another coefficient times the last measurement value that we had, and plus a residual term. So based on this idea, we have 8 model parameters to estimate for each of the lead time k if we design different models for different lead time. These weights are the linear coefficients we have here, and we would like them to vary as a function of lead time, but also to be forced to 0 if they are not really necessary to explain what's going on and to be used as input to forecasting. If we apply this idea and we focus again on the example of the 28th of April 2002, as for the other blocks, we use the last 600 values, so the last 600 observations. We have the weather forecast also. So over this time window of 600 values, we find a relationship between these features that we described in the previous slide and the response variable, and we get lasso estimates for these beta parameters. They are computed as a function of the lead time, here between 1 and 48, and this would be the coefficient value in per unit. Right. So if we were to look at this various coefficient, we see that a lot of the coefficients are equal to 0, which was the purpose of the lasso. It really forced these coefficients to be pushed away if they were not significantly useful for forecasting. And then for a few of the coefficients, they are non-zero. You see here, for instance, beta 0, which is the intercept, is non-zero for most of the lead times. Beta 1, which is the coefficient associated to the wind speed forecast, is also non-zero for most of the value, for most of the lead times. Then we also have the second coefficient, beta 2, which is non-zero for some lead time, and it's associated to the square value of the wind speed forecast, etc. So using this lasso estimator, we can input a lot of features, and by doing this estimation, it does somehow an automatic selection of the features that are of interest and also find the linear coefficients that are to be used for forecasting. The resulting forecast that we have here, so for the example of the 28th of April, like before, we got our necessary vector and matrices over the 600 values. We got the coefficient that we estimated from before, and here is the result. The forecast is shown in red, and the measurements that were obtained a posteriori are here in black circles with lines in between. In this example, something that we didn't see in the previous cases, obviously they were a naive and benchmark approach. Here we have some dynamics in the forecast. There is some weather forecast information input. We have some more advanced models with coefficients that change with the lead time, with various type of input variables. So we expect a bit more flesh, you could say. It should be performing a bit better and with more dynamic component. Still, the forecast doesn't look that amazing if we just look at this example. But eventually what we have to do is to apply this strategy for a whole year. So that would be the sample year of 2002, like for the other methods, and we analyze its performance. We use the same metrics as for the other cases, so we have normalized bias, mean absolute error, and root mean square error, and we compare with the previous forecast. So the bias here, that will be the dotted line, which fluctuates around 0 as a function of the lead time. And actually what happens is that it is somehow 0. These fluctuations are more sampling effect as we consider a fairly limited period. Then these are our mean absolute error and root mean square error for our forecast. And this is the reference that we got from the previous block by combining persistence and climatology. So remember already with this combination of persistence and climatology, we got a fairly good combination and the performance was fairly good. This is here with RMSE varying between 8% and 25%. Still, considering our more advanced forecasting approach here with the lasso estimator and all the input features, we obtain the RMSE as this red curve, and this is a fairly significant improvement over the reference. For comparison, we also see the mean absolute error here that is, as intuitively expected, lower than the RMSE, but it cannot be directly compared to the other ones. It seems we have substantially improved, but still I believe we could do better, and this is why we'll invest in more advanced forecasting techniques and modeling techniques in the next module. So now I would like to invite you to use the self-assessment quiz to check your understanding.